air cannons as a flow aid. We have many different types of versatile systems that can help with problems that arise across many different industries and many different materials, such as coal, fertilizer, glass, cement. Depending on what your industry is, if you're manually intervening, air cannons are a proven solution across the globe. We've been doing this for many, many years. Martin Engineering actually started in 1944. So there's quite a few years of experience providing solutions for a safer, cleaner, more productive material handling systems. And we're here to help if you have issues with material flow. As we go through, what I'm going to do is I'm going to pass this over to Mike Masterson since he has 29 years and 10 days with Martin Engineering and he lived the timeline. So the floor is yours, Mike. Please elaborate.
Well, this just goes to show some of the advancements we've done over the years. So, and then in the 70s, they came out with the compressed air style of air cannon that we use. It's got the common animal that's on here is a 4-inch discharge air cannon. We've had customer input along those years to meet different needs, expectations, and we've keep developing the product. So as you can see from the 70s, 80s, 90s, and so on, and now we've had the hurricane and the typhoon. And basically the difference is just how the operation works, but the performance and the package is still the same between the two different styles of cannons, but it's customer input and product development is what we've been doing as the years show in this timeline.
Perfect. A lot of things that we have learned over the years of what works and what doesn't work has brought us to our current technology. And again, a proven method for providing material flow without manual intervention, providing safer material handling. As we go through, the first thing that I like to do is a picture's worth 1,000 words, where a video's worth a million. So what we want to do here is I want to show you an example of the amount of force that's provided with 100 psi out of our Martin Engineering air cannon. So I'm going to go ahead and hit play here.
This is just what frozen grapefruit on
Yes,
steel plate.
pretty impressive. I like to play that twice just because it's really cool to see the amount of force that we can create by releasing that stored energy from the air cannon pressure vessel and providing that as a material flow. Keep in mind with the air cannon systems, we can manipulate that blast force by simply increasing or lowering the PSI. So we can actually cater our blast force to your specific application, just enough to provide material flow without causing structural damage or any other issues, fugitive material and that kind of thing. So we can actually manipulate that. I do have another video I'd like to show you as an example of the blunt force of an air cannon being fired. This is an 8-inch cinder block. And as you can see, that is just air that is doing that to the block.
We took this video when we were developing the hurricane, and it was to show that we've taken another big step in performance, energy from point A to point B. The traditional style of cannons and how they would operate and their speed wouldn't make any difference on this, that they would go around. But the point now that we can open this valving so quickly, all that compressed energy is discharged instantly. That took the hurricane, that really brought the game up to change as far as air cannon performance and controls. We'll get into the controls a little bit later, but it's things to consider when you're wanting performance of this compressed air and the work you're wanting to get done.
Perfect. Thank you, Mike. I appreciate that. As Mike said, we're going to talk about controls. What we're actually going to do is we're going to go through some various different applications through the years that we've provided solutions for material flow. This is more of a 50,000 foot level of, a smart series approach for material flow. And the ability that we have to basically cater to your specific application to attack the root cause of where that material is building up and causing that material to flow and not causing problems with your production. This particular example basically is a conventional transfer point, basically head pulley with a belt cleaner primary and secondary. The problem with this particular application is material being heavy laden with moisture content will accumulate into the head chute, basically start climbing on itself and get up into the head pulley and into the cleaners, causing a huge fugitive material housekeeping issue, in which manual intervention has to be implemented to keep the material flowing and also cleaning up the material that's not going where you actually want it to go. So what we've done here is we utilized air cannons to proactively keep the area clean and prevent material buildup. And I said one word, proactive. In the air cannon world, proactive, not reactive. We keep things clean and moving and stay ahead of the buildup. That's rule number one. But as you can see in this particular application, this is what the plant was dealing with material building up inside their head chute. And we were able to not only put in air cannons, but we can also use certain type of nozzles where we can shape that air and sweep slopes versus a blowpipe. So we have different types of nozzles that we can utilize to attack those type of accumulations and again be proactive and not allowing that material to build up, causing issues. And we'll go ahead and go on to the
One
next ones. If you
one
do,
question on this one, Mike. What we don't show is the nozzle location. But basically with head chutes, there can be many different ways of placing the cannons to kick out the foothold. But that's the name of the game. We're going to kick out the foothold where this material builds and stacks on top of itself. So not every two places are exactly the same as far as their buildup.
good point. That's a great point because a lot of times that material will react differently. So a lot of times when we actually look at an application, we're going off the information provided by the plant of where that accumulation is starting. Again, just like Masterson elaborated on, removing that foothold and allowing that material to build. We're going to go ahead and go to the next one, and this is a cone application. And I'm going to go ahead and let Masterson kind of explain what's going on here and what we've done here to provide material flow.
Well, this shows a typical cone section, and it can be many different materials. I think it was an iron ore band for a cement plant. But it shows how many things we've tried to finally get to where we had a solution. Sometimes we call it the Band-Aid fix. How many things did we try to do? But the final solution here was 3 air cannons, basically in a ascending spiral pattern. So as you can see at the end of the cone where the discharge is, that's basically like a bottleneck. We need a tension there. If the material starts to bridge on the lower part of the cone, we've got a couple of cannons to knock that out. And typically this was having a problem on the very lower third of the cone section. But the customer had tried the electromagnetic vibration. It had tried hammer rash, Cardox ports, aeration lines above the cannons, and poke hole doors. So they are poke hole ports there. So anyway, the main deal was setting the cannons there in the right place, automating the system, and firing it when they need to, knocking out the bridging material, and now we have production on a reliable basis.
Perfect. This particular application, like Masterson said, you have different types of flow aids initially, where the last right of refusal was the air cannons, and they do the job and provide the material flow. The next application is your typical transfer points. This can be in any type of industry as far as materials. This particular transfer point, our material here is coal. Basically, the problem is coal is being railed in across the country. Weather, rain makes the coal wet through the transport through the open rail cars. The rail, basically the trains come in, dump the coal through a series of transfer points, trying to get coal up to the power plant to be burnt for the turbine. The problem is when you have that high moisture content, the material wouldn't flow, and all these transfer points would become plugged with wet coal. So our solution here was to provide a material flow aid, such as air cannons, to provide a proactive approach in blasting in a sequence that kind of links into our smart series approach to air cannons, just like the cone application where Masterson mentions a domino effect. Same thing, the lowest air cannon will fire, clearing the throat. Next cannon will fire above that in a sequence as far as how we control them. One thing that you might notice on the right-hand side is one of the struggles that we have with material flow aids and putting air cannons in. A lot of times the air cannon can be mounted in a place where you cannot get to it and easily repair the valve assembly when it wears out over time. So one of the things that we can do is we can actually position that cannon uh, further up through grading or put it in a position where you can easily get to the valve for service. That's one of the things that we look at very closely is one, putting the cannon in so we can provide material flow, but two, having the cannons accessible so we're able to service them. But this is a good example of us fighting severely wet coal, providing the power plant to actually get the coal up to the power plant and to the bunkers to burn coal for making us all power. I'm going to go ahead and go to the next one. This is a coal feeder turbine inlet, and not that I'm all monotone. I'm going to let Masterson kind of explain what's going on here.
Basically, it's the feeder for the turbine, and they have a leveling bar, and the leveling bar for the material feed was collecting material, and also up in the cone they had periodic problems. So this was basically shown on the left, a cannon that's going to blast the cumulative larger pieces that will choke off the leveling bar in the feeder. And then anything that's going to get the transition to lower cone, it's got the cannon up there. So this has got a lot of material going through it daily, but it's a two cannon solution to make this reliable. Prior to the cannon, the guys had to go into a small little poke hole port, and they had to rot out the chunks of coal that were choking off the leveling bar feed. So it was an operator system that was done manually, and they have automated to where when the feed is less than 100%, they can fire the cannon. So it's automated now and reliable.
That's a good example of the versatility that the air cannon systems can provide. We can provide a manual solenoid initially, where you can fire them manually from a safe spot where we mount the solenoid, uh, providing material flow. And once proven, we can actually have that automated through a single timer. If we have multiple cannons, we have multiple bank timers where we can fire them in sequence, or you can link them through your PLC program logic. That way, you're able to manipulate that blast sequence. And again, I got to fall back to being proactive. You can fire too often, but you can also fire not often enough. So always want to keep in mind that you want to stay ahead of the buildup. And a lot of times we look at applications where we talk about what's called the sweet spot. We got our PSI for blast force correct. We've got our port placements in the right spots, and then our sequencing. All those tie together to provide a good system for your material flow problems. Here's another example similar to the turbine inlet. This is basically just a hopper application. Again, reiterating the domino effect. The lowest cannon will clear the bottleneck, like Masterson mentioned in the other previous slide. And then the upper cannon will fire after that, providing this proper sequence. Every material is different. At a plant level, you can pretty much know how often you're going to fire it based on material flow. It may fire every 2 minutes or it may fire every 15 minutes, depending on moisture content, types of material. So there's a lot of variables that go into the Canon applications and systems, but we're able to provide what we call the sweet spot, getting our PSI right, our ports in the right place, and of course, sequencing. And then our next slide is for anybody that's having vibratory feeders or a live bottom cone. I'll let Masterson kind of explain what we're doing here and why we do this here.
Well, as you can see, the live bottom was having this problem with the metered feed that they had, and the workforce there was heavily on the hammer rash. So the solution was, let's get a cannon in there so the guys aren't swinging over their head, creating injuries. And that's what the real problem was. So we had to isolate the vibration from the cannon with this flexible discharge. And this is a specific style of flex hose that we use for the Hurricane because of it has the stepped up performance. But as you can see, we isolate it. The cannon is mounted to the I-beam above, but the rotation of the live bottom is being isolated on this flexible hose. This was planned to have 4 cannons on it, but the one worked so well, they just left it as 1 cannon. So sometimes we don't know how much effect it will do for promoting flow. In this case, it, it really was high performance on getting the job done. But just an application showing you how you can isolate the cannon from the vibration. The two don't play well, and we use a flexible discharge hose.
Good point. Yeah, the problem with vibration is it actually attacks the welds on your pressure vessel. Vibration can cause issues with your valve assembly. That's like Masterson said, we provide that 4-inch flex line to absorb that vibration, providing a long-lasting cannon system that you don't have to constantly repair. Our next one, I'll kind of let Masterson explain what we've done here and the options between two different types of nozzles.
This is a square cone. So I earlier showed us, a round cone and putting cannons in an ascending spiral. So here we are. The picture on the left is showing cannons that are sweeping across one side, one flat of the square cone. And that's an angled fan jet. It kind of takes the cannon, elevates it a little bit above the port, so material's not coming back into the valve assembly. And we sweep across those flats, and that stops the material from arching and bridging from one side to the other and keeps the material going. On the right side is another square cone. It's a little bit shorter in its height, but we have just a blowpipe in the center kicking out the bridging material that's right above the discharge to the belt. So knowing exactly where our arching material is, where the buildup is, we can place cannons in that material, kick out its foothold, and we can do it a couple different ways. Both of these work and both of these get the job done. Sometimes we have to shear the flat and using the one of two styles of a cannon blast, a fan jet flat profile blast or a round blowpipe for just the brute force of knocking out bridging material. This shows both of them getting the job done for the information that we receive about the buildup problems and the problems of no flow conditions.
Well, that's a good point. So the nice thing about the air cannon world is one specific nozzle works well, and then another specific nozzle works well as well. It really depends on the type of material that you have and the moisture content, but basically the versatility of how we attack it is crucial to your production. The next application is basically in your aggregate world. This actually internally, this is a what we call a rock box. So there's a series of steps inside where material, basically like a material deadbed, material will flow through that transfer point on that rock box application. We've installed 2 air cannons. Kind of imagine a double barrel shotgun firing sequentially as material is being conveyed. That material will accumulate again through moisture content, uh, basically plugging up the transfer, causing all kinds of problems, not only for production but manual intervention. With this particular system, we were able to provide that double barrel air cannon blast, keeping that rock box clear, basically that transition onto the belt below, and removing manual intervention and providing material flow to increase production. All right, here's another example of a coal transfer point, and this is a little more close-up picture of what Masterson was elaborating on the hopper application with a 30-degree fan jet nozzle. Basically, a flat plane sweeping that slope or shearing the wall to provide material flow. Works very, very well. Certain applications will dictate this type of nozzle versus a blowpipe. And again, sequential firing enough to provide material flow where we're not actually over firing. Our next application, again, I want to kind of reiterate that this is kind of a 50,000 foot level approach of introductions into air cannons and how we use those as an material flow. So I'll let Masterson kind of explain what we're doing here with this truck dump.
So this is a truck dump that basically had the issue of when one truck dumps, there's not enough capacity for the next truck because it's only being pulled out the center drag chain. So as you can see on the right side, we got the two piles of material right and left, and on the left side, we've actually had a blast here where it's kind of making the material start to fall. On the right side, it's rock solid. So that capacity is being taken up and causes delays in the truck dumping and production. All right, let's put air cannons in. So on the left side, you can see the cannons. They have 6 ports there. And the reason we did was because we weren't sure exactly where the sweet spot was to knock down those materials. So we added extra ports. Back to as Mike said, you've got to have everything work together. So we picked a certain size of cannons. We knew that the style of 150 liter or larger hurricane is what we need for this large application. Where we put them is B, where we're going to put this blast. We've got A, the air cannon picked out. B, where we're going to put the blast. Well, we got options to fine tune here. And then C, it was controls. What works on the truck dump on the controls is all 4 cannons. So what the final positioning here was 3 on the bottom and 1 on the top upper right. All 4 cannons blast exactly the same time. So this is one group blast that makes that wall lose all of its strength and collapse. This is exactly what they wanted. They didn't need rocks going across the quarry area. So it makes this whole world slump. So it was the right cannons, the right location, and the right way of blasting made everything work like it's supposed to. So that was a solution on this one, and it's a solution for all applications. We can put cannons in, but like Mike said earlier, it's when you blast them. Too often, not often enough. All that has to be chosen by the customer of what is the best for the process. And we can give you examples right and left about how this was too much, this wasn't enough. Pressure wasn't enough, pressure was too much. You have all those options, especially with a hurricane. The range for PSI that it'll operate, how accurately it can operate in a group, the distance where the solenoid is located versus the operation and location of the cannon. All these things are maybe a different day or a different time to understand, but these are huge operational benefits you have for these cannons.
Here we have a primary crusher, and this system was actually put in by you, Masterson, how many years ago?
Oh, we did this back in 1912. Yeah, all it was is a crusher. So they have this called beater bars on this crusher, and they have material that will build up in certain cavities, and that's typical for a lot of crushers. The material builds up in the cavity. It's not so much that it's causing other problems as it is causing premature wear for no reason. It doesn't need to stay there. The material's gone, but we have clay and other materials that are stuck in these cavities that will wear out the crusher. So we empty these cavities, empty these areas, empty any potential buildup that causes extra wear and tear. So for crushers, it's mainly getting rid of the leftover residue that's not flowing through.
So this next application is a copper mine transfer point. And again, Masterson, with his 29 years of experience, installed this particular application. And if you look at the picture on the right, I think that links a little really well with your truck dump question of how we're penetrating into the material, providing flow. So I'll let you kind of elaborate on that as well, Masters.
The customer problem was material would build up, choke off the transfer point, and stop all production. Yeah, and this happened to be copper, $50,000 an hour, almost 20 years ago. I think this was back in '08 or '09. And basically, what they did is these dead bed, the rock beds. We buried the cannon pipes in there, and we keep blasting it. It stayed fluid. It kept moving. It never had anything to build upon. So this is a return on investment basically over the weekend. If they didn't have a choke off on this transfer point, the cannons paid for themselves. It took many hours to clean this out. Once it did block off, and the material that was in there is amazing how it was like concrete. This is 2 or 3 days for the production team to come in and jackhammer this out so we could put cannons in. But anyway, transfer points. This is on large scale. This is probably somewhere in the 60-inch belt or more that's moving out of their pit, and but they have a lot of cannons and a lot of transfer points in this area for how much material they move. So no messing around there. They want production.
Perfect example of a smart series approach to material flow utilizing air cannons. This next application is a stockpile application. As you can see, on the left-hand side, we actually have the cannons mounted underneath where the material is actually being dropped from the stockpile onto a conveyor. Above, we actually run those pipes up and basically eliminate the rat holing that you have with stockpile applications and widening that throat so we can provide production. And then again, same thing, being proactive, getting your sequential firing correct, port placements, and PSI levels. If you notice on the left side, generally we have where the pipes will come in horizontally, preventing material to fall back into the cannon itself. If we do have material that does infiltrate the pipe, Masterson has what we call the clean out tee, so we can remove those blind flanges, clean out any residual material that may have gotten in there. But we try to prevent that through installation so we don't have material infiltrating the cannon or the valve assembly. That's probably the biggest rule with any air cannon system. The air cannons must be elevated. Gravity will cause dust. If it got a cannon upside down, gravity will fall into the valve assembly and causes all kinds of problems with the valve assembly operation because material is infiltrated. So when we do install systems, we look very close at that on how do we keep the air cannon breathing and prevent material infiltration from basically rendering your air cannon inoperable. This is at a foundry. This one I did probably 5, 6 years ago. This kind of reiterates of an application that we came up and we weren't sure if this was going to work, and we tried it and it did. Basically, what you're seeing on your left-hand side is the castings are poured, and those are rollover cages. So when it goes into the rollover station, the cage would roll over and the sand was supposed to fall off. The green sand is what they call it. Basically, because it was packed so tight around all the crevices around those parts, one rollover did not clear out the sand. So then they made additional rollovers to the tune of 5 or 6 times these rollover cages had to turn over to dismantle the green sand that provided the moldings for the parts. The problem was is that as many times as they were rolling that over, the parts were dented and dinged, and it was a quality issue. So what we did here is we actually provided a series of cannons right after the first rollover and broke that bond of green sand around those parts. And if you notice on the right-hand side of the picture, this is the versatility that we can go to the extent with the air cannon system. We're actually filling from the side of the pressure vessel along filling at the top on the valve assembly. So what we can do is called a rapid fire. So we can fire quickly a couple times to disseminate that green sand buildup around the parts. providing a solution for the foundry and worked very well. This is a good example of uh, we're not really sure what will happen here, but let's put cannons on it and see if it works. And a lot of times, well, I'd say 99% of the time, we have a solution. There are do's and don'ts with the cannons, and that's a separate webinar. But generally, we're willing to try to help solve whatever problem that you're having utilizing our air cannon system and going from there. So this is a good example of the versatility that we can provide. The next application was a biomass feeder, and Masterson did this one as well with his vast experience. Kind of explain what was going on here, if you can, Mike.
This is basically stringy wood bark material. And like we showed earlier, beginning of this was the leveling bar at a coal feeder before it goes in the turbine. Same principle. We take the material, as you can see on the picture here towards the right, below the cannons is a couple of screws that are dragging the material down to the hopper. The material feed has to be specific. Without it being correct, they don't have the power. That's what they're there for. So when they were getting 80, 70% material feed, that's the power they were getting. The rat's nest of material on the leveling bar, all we did was put two cannons there, and you can see in the very far lower right, the cannons just blast that material back up into the system, and the leveling bar now is back to a 100% feed. This was so worked so well. It was the expedite. We had them. I think I was there on a Friday. Canon showed up on a Saturday morning, and they installed them. It worked so well over the weekend. They repeated the expedite process of the next two other feeders and had them all in by midweek. So it was something that was very successful. And all it was is taking this problem that happened constantly, and they automated it, and now it was taken care of.
Nice. Thank you, Mike. Same thing with the pulp and paper combustion chamber. Masterson actually did this one as well, and he can kind of explain what we were doing with this type of penetration and what we were doing to provide material flow.
So yeah, it's a fluidized combustion chamber, and basically, we got your down in the center of this whole chambers is your fluidized bed, and the material would slag up and build up on that 55-degree angle of the slope above the center of flame feed. When the large pieces of slag would fall down, they would choke off the flame. So they wanted to break up the slag. Like a lot of pyro processes, it's not symmetrical. They get this and that happens only on one side. Well, 180 degrees of this built up slag. The other side did not. And as you can see in the middle center of the picture, we're just shearing that material before it gets too large to cause a problem. It's broken up and kicked back in. The replenishment of a fluidizing combustion chamber is they're always moving that sand, moving that material. So they need smaller pieces. So this was a little bit of a complex install, but it was something that's done for the paper industry in Mississippi.
Yeah, kind of reiterates the proactive approach, not allowing the material to basically block the discharge. So staying ahead of it, providing material flow, utilizing air cannons. Next application. This is an SCR application in the power plant. Basically, in the power plant world or coal-fired power generation world, they don't necessarily call these air cannons. They call them ash sweeps. What's happening here is as they're burning coal, it produces ash, which also provides SOx and NOx, sulfuric oxide and nitrous oxide. So there's layers of catalyst that has a chemical reaction with the ammonia that's injected to reduce those emissions for the power plant. The problem is as they were burning the coal, the ash accumulation would basically blind off that catalyst layer and not allow it to, exhaust air, kind of like a catalytic converter on your car or truck. If that gets plugged, you lose your performance. So basically, without derating the plant, if they didn't have the air cannons, that ash would build up and blind off their catalyst, basically suffocating the emission system, So we are able to come in with a Smart Series nozzle, which provided that sweeping tight blast that sweeps that catalyst floor, blasting that ash back up into the airflow and re-entraining it to be able for it to have that chemical reaction, reducing the SOx and NOx emissions. Um, Done this on many, many different power plants across the country. Proven method, works very, very well. We'll go ahead and go to the next one. This is the 360 retractable. A lot of times we have air cannons, depending on where we are putting the port, we may not be able to get it from the side where you have a big structure and we have material accumulation in the center. We can actually come in with the penetration and attack an area which you normally wouldn't be able to get to from the side. So if you notice on the right-hand side, we have what's basically a sand table that mimics this 360 type nozzle that has a blunt tip on it with ports north, south, and east and west. When it blasts, it's cleaning that wall surface and preventing material buildup.
What's different with this system here is that we have, an active moving nozzle assembly. So it's got its place for doing uh, specialized cleaning. And we've developed a couple different ways of controlling it, how it strokes and how the whole system works. So if this is something that's appealing that, you can't get to this area because the cannons on the corners won't reach it, it's in the center of a wall that has an area that has to be cleaned, and we mount to that wall and we clean that vertical surface area. If this is something that makes you scratch your head and say, I think we could use something like that, there's a lot to learn about how it operates, how it cleans, and how you would use it. So we can help you with those questions because it gets kind of detailed. We've gone electric solenoids, pneumatic control, and so on about how it strokes and fires all at once. So it's got a little bit more than just a simple one cannon, one port, one blast.
Yeah, thanks for reiterating. Like I said, it's 360 retractable. What's happening is actually that nozzle is penetrating into a high temp application, blasting that material buildup, and then it retracts back into the port, uh, saving your nozzle from being extended into very high temp. We do a lot with the cement industry. That internal temperatures can be anywhere between 1500 to 2300 degrees. And this allows that nozzle to last the duration of a campaign for them to extend, blast, and then retract. If you do have material flow issues and would entertain the idea of utilizing air cannons as a flow aid for a cleaner, safer, more productive material handling system, we're more than happy to provide our expertise and do what we can to help alleviate those issues. Again, please feel free to reach out to either myself or Mike at any time, and we'll be more than happy to help you out. Thanks, Mike Masterson, for your illustrious and elaborate experience. It's much appreciated.
Just trying to
And
help.
yeah, I want everybody to have a very safe day. Thank you so much. Appreciate it.
Thank you.